All right. So I'm going to talk about the JWST pipeline and data products. Unlike what Alvaro said, I'm not going to go into that level of detail. It's going to be very high level. If you'd like more detail, we have places for you to go. So basically, I'm talking about how you get from raw data, and then I'm going to go through the 3 stages of the pipeline fairly quickly: ramps to slopes, calibrated slopes, and ensemble processing, and then what goes in the archive. I will point out that the data reduction, we really are standing on the shoulders of previous missions. Hubble, Spitzer, Herschel, and ground-based observatories and instruments. And I would say that we're learning what to do and what not to do, right? So I've been on previous missions. Some things we made very good decisions, and sometimes we didn't, and we're definitely learning from that, I would argue. So here's the general pipeline architecture. If you'll notice, one of the key things here is you do not see the instrument names in this pipeline. Since we're doing 4 instruments and they're coming online at the same time, there's a lot of shared capabilities, much less shared detector technology. And so we're attempting to use, where it's reasonable, we're using the pieces that are the same. Okay? So really, Cal Detector 1, that's where we go from ramps to slopes. Fitting a line to a ramp is pretty much fitting a line to a ramp, right? Everybody has to do very similar things. They're not all the same. There are parts that are different. You know, the nonlinearity corrections are different between the near-infrared and mid-infrared. That's fine. But in general, we're using very similar code for all that. Now you can see in stage 2 where we're actually calibrating the slope images. We split between imaging and spectroscopy. Those are different, and so we treat those 2 differently. And then we get a little more specific down at the bottom, and now you can see kind of all the various instrument modes: imaging, chronography, aperture masking interferometry, TSO, and spectroscopy. Okay, so that's the overall, that's the high-level version of the pipeline, and we've got each one of these has lots of steps in it with lots of details. But I'm not going to go into the details because A, it's right before lunch, and you guys have already had a lot of information. So there are details, and you can talk to me if you want to get involved. Right, I got to stand here. So I want to talk a little bit about how we've assembled this, right? There's a lot of potential information, a lot of ways we can figure out how to reduce it. We're trying to be a little measured in what algorithms we adopt, so we're trying to adopt the best practices. And so how are we doing this? Well, we're getting lots of information. So this is kind of the workflow, and I'll step through it. So how do we start with? We start with the instrument teams are providing us with the majority of the inputs of what we should do. They're saying, okay, please use this algorithm to do this part of the pipeline. This is, these are where the instrument experts are. This is where extensive ground testing is being taken into account. Some of them are in the room, some of them aren't, but that's where the expertise is. There's 3 special case inputs that we get for these sets of kinds of observations: chronographic time series and moving targets, that really realized these were specific science cases that needed expertise from the instrument teams as well as some external expertise. And so these working groups were constituted. And the instrument team said, yes, get your inputs from these working groups. And they're members of these working groups. And so that's kind of where all the input comes into the institute of, here are all the requests for how we should reduce the data. I've been very careful to call them requests for how to reduce the data, not requirements, because sometimes they're conflicting. Or sometimes one instrument team has been working very hard on one step and another instrument team has not been, and we can use that information, and the other instrument team will take a look at it and go, yeah, that looks good, let's use that. So we take all these inputs and we work. This is the JWST Calibration Working Group, which is the working group I lead, which has got, I don't know, 50, 100 members on it. It truly is herding cats, I can tell you that now. You get enough PhDs in a room and it's fun. We do a critical review of the inputs we get. We actually do ask questions and make sure we understand them and we understand what people are telling us and that it is a good idea. Identify the common steps, encourage cross-pollination, encourage cross-instrument development where it's appropriate. Where it's not appropriate, we don't do it, right? We're not fitting everybody into the same round hole, into the square pegs into round holes. We use whatever holes are needed in order to fit the algorithms in. And then we need to decide on what the algorithms are for development. And we are resource limited, whereas requests are not. And so we do have to play some games there, and I'll talk a little bit about that later. We want to get everything in the best we can do. Unfortunately, we're not paid an infinite amount of money, and we don't have an infinite number of people to do it. So what do we do? So we've made our decisions, then this moves on to another working group. This is the pipeline working group. This is composed of scientists and programmers, and they actually, so in the calibration working group, we decide on what the algorithms are. And then the pipeline working group works with the programmers at the Institute to actually implement them, test them, verify it works, and give feedback to the calibration working group if we've asked for something stupid or something that's not implementable. And then we have to say, okay, let's think about that again, let's poll the experts, let's figure out what we can do within our reasonable resources. And then the people who actually do the coding, I've done the coding on the MIPS pipeline in the past for Spitzer. It's a lot of fun, but I don't get to do that anymore, and that's probably a good thing. So we have the science software branch. These are actually professional coders. They really do different code and better code than we do, often. And so they have to write the pipeline. From a scientist's point of view, the writing the pipeline is the algorithms. From an actual getting a production pipeline to work in a production environment, that means you need to integrate it into the data management system. It has to be able to run lights out all the time. There's a whole bunch of bookkeeping code that we don't usually think about that is actually critical to the pipeline actually working. And they will actually use code that's delivered in earlier stages, especially if it's in Python. And that is, they really like to see Python. As coders, they understand Python often better than English. And I'm the same way, because you have to be much more precise in code than when I say, yeah, just apply that nonlinearity correction. That's not the same thing. So that does, let's see. So this is the nominal workflow. It looks nice and clean. This is really what the workflow looks like. There's a lot of feedback in all directions. There's a lot of contacts at every level between the external teams and the internal teams. So it's a messier than our nominal, but this is what in reality what works best. The development plan, we've split it into two pieces in order to make sure that everything works. So the first part we do is make sure we're going to do the baseline pipeline. So that means all instruments in all modes will be able to reduce the data and get high-level, high-quality science data out the back. It meets requirements. That's another thing you have to do when you're on missions. I'm less excited about requirements. I liked it when I was on the instrument team and I didn't have as many requirements I had to deal with. And the goal is to deliver the baseline pipeline at the end of this year. Right? So the code is being delivered at the end of this year. Now, that's not the best possible reductions. So we're also already starting on what are the algorithms for the optimal pipeline, or maybe you should say at the upgraded pipeline or the expanded pipeline. You can pick your word that makes sense to you. And these would be the best possible reductions we can do as a community. Highest quality science data, but really the optimal pipeline is something we'll have done after the mission is over. Right? We're going to still work on upgrading the data reduction algorithms all the way through the mission. So this is a target, not an end. We started work after the baseline pipeline is done, and as I said, continue to the end. So the calibration working group, because since we decide on algorithms, we're already starting to think about what are the optimal algorithms while the science software branch is coding it. Okay, because we're out of phase, right? We're at the beginning of the process in a sense. So we do need to prioritize effort, and so I'm always interested to hear more what people think is important. And I'll give you an example. Almost there. I'll give you an example of a couple of the algorithms we're thinking about. So just a little bit about the pipeline. It's written in Python, based on AstroPy. In fact, JWST is making significant contributions to AstroPy to support the JWST pipeline. It's, I think, pretty easily configurable. Users, you can rerun all or part of the pipeline. You can replace specific modules with something you think is better, and then run it. So this is one nice thing about this pipeline. It is more configurable than previous pipelines I've had experience with. It's hosted on GitHub. It's already there. Okay? But it's the development version. You're seeing what they're working on today. So you should be, you're not getting a final polished version at this point. It is interesting to look at, but be warned, it's going to break and it's not going to work as well as you'd like it. Wait till there's actually the baseline version delivery, and then there'll be a completely functioning pipeline. Okay, so I wanted to talk a bit about data products. That's the slide that's missing because we're using an old version. I'll mention it even though I don't have a slide. So what's the baseline pipeline is think about straight reductions. For say spectroscopic extraction, I'm just going to do boxcar averaging with an appropriate aperture, right? But maybe in an optimal pipeline, we should be doing something like optimal spectral extraction, where I use knowledge of the spatial profile to improve my flagging of cosmic rays and variable hot pixels, as well as weight to get an optimal signal noise. It's a technique that's been around for many years. We'd like to put that in, but we can get really good science out of a simple extraction. So that's one of the things we're working on. One of the other potential ones to go into the optimal pipeline is moving away from weighted least squares, weighted linear least squares to fitting a ramp, to doing generalized least squares, which allows us to do better with correlations and do a bit improved cosmic ray detection on the ramp. And there was one more I was going to add in. And MIRI has some small drifts, and so self-calibration is something we're trying to work on to get into the optimal pipeline. All these things, these are 3 out of about 15 things that we're thinking about right now for the optimal pipeline. We're not going to get them all in before launch, and so we're going to prioritize which ones we think are the most important ones and work on those and try to get the instrument teams to tell us as much as possible and get it moved through the system. And I've, of course, given you the 3 that I think are particularly interesting. But I'm only one person, and we'll see. This is discussions in the calibration working group over the next couple of months. Okay, so what about data products? So that's kind of an idea of how it is. What are the data products? What are you going to get out of the pipeline? Of course, you can always have the raw data. No one's going to, the raw data is available when it hits the ground. There's intermediate stage data in the pipeline, and there are various parts of the pipeline. You can also run the pipeline offline and get lots of intermediate data, right, at each step if you really want. But in the end, so the final data we're trying to get is the best quality we can get from an automated pipeline. If it might be perfect for your science, it may not be. You may want to do things in addition to make it better. In Spitzer speak, this was called browse quality. You can at least look at it and see what your data look like, give you a really good idea of the quality of the data you're going to get in the end. It's going to be flux, wavelength, and astrometrically calibrated. I've already said that bit. I will point out the calibration of flux, wavelength, and astrometry for JWST is all being done as a unified program for all 4 instruments, right? They're not independent calibration programs for each instrument. There's one calibration program that's going to do all instruments simultaneously. So we should have, this guarantees we have very good relative calibration between the instruments. So the near spec IFU should match the MIRI IFU by definition, which will be nice. Imaging products. So we'll have mosaics of all of the images in the same filter. They'll be in sky coordinates. We'll also do a catalog of sources, automated, the best you can do in an automated generation sense. At the integration level, so the individual, not exposures, but integrations in an exposure, the images are fully corrected with flagging of the cosmic rays, etc., in both detector and sky coordinates, rectified coordinates. And I can give you an example from MIRI. I'm on the MIRI team, so you're going to see all the examples are from MIRI. What can I say? So this is just a simple, this is standard mosaicing. You have a whole bunch of images, and you put them together into a mosaic. But it's at least a visual to wake you up just a little bit. Spectroscopic data products for slit and slitless. There'll be a 2D spectral image, so with dimensions of a long slit and wavelength. And this includes, that should say MOS, that's one of the corrections I made, any of the multi-object spectrograph modes, both slitless and with the near-spec slits, right? So each of the isolated sources are treated like an individual source, and so we get that straightforward processing. For the IFU, we'll have a spectral cube, an RA deck, and wavelength, or sky coordinates. If you pick some different coordinates, you can get it run in that. We'll also do an extracted spectrum of the target source. And you will be able to say whether or not your source is pointer extended in APT when you set up your observation. And that is advice to the pipeline on how to do the spectral extraction and what calibrations to use. Particularly important for near spec. At the integration level, you'll get all your images fully corrected, again with the flagging of the cosmic rays. And in the sense of, the nice thing about the flagging of the cosmic rays at this step is you can also do it from the ensemble, right? From the stack of data. You can flag more cosmic rays than you can just flag on the ramps. You also get these detector and sky rectified coordinates, and you'll also get 3D cubes or 2D images, depending on the observation type, for each integration. Okay. This is a nice visualization of this for the MIRI IFU, and so you can actually see there's on the bottom bit. There's your individual exposure level. integration level in detector coordinates, and then you'll get your spectral cubes, right? And each one of those is for a different channel. You'll even get one all combined, right? It's going to be not a small data product, and challenging to interpret, I think, with the changing wavelengths, as Tracy, a changing size of the PSF as a function of wavelength. For chronographic data, you'll be getting co-added images. Now, this is done in detector coordinates, right? That's the chronography we're not mapping onto the sky. And this is done after PSF subtraction from each integration. At the integration level, we'll show all the images fully corrected with flagging after PSF subtraction. And this one we will do in detector and sky coordinates, mainly because we can. And here's an example of that from the MIRI 4-quadrant phase masks. All the way over here, you see that this is just the direct image. And then once you put it through the chronograph, the 4-quadrant phase mask, of course, you suppress the central source. Here's your target. Here's your reference source. Co-add them together and subtract them. There will be more complicated algorithms as well. And then you can start to see things. Okay, so the goal is, as I said, to get people going, browse quality. You probably will work offline and get better quality out of it, but at least this will get you started. Aperture masking interferometry is the fringe parameters, which is the closer phases and amplitudes and reconstructed images, although the image reconstruction is an optimal step where we're going to try to work on, where you actually try to make an image from the different fringes. Time series observations. For photometry, there'll be aperture photometry per integration. Spectroscopy will extract spectrum from each integration. Then there'll also be a white light photometry per integration. So that's just where you take the spectrum and collapse it. Easy. We can do that algorithm. It's nice when they're easy steps. We'll also provide at the integration level the image or spectral image as appropriate, fully corrected, both in detector and sky. And I should have put on here, in addition, for TSO observations only, we will also be archiving and providing the ramps corrected, but before slope fitting. Okay, because that's something that the TSO community in particular has asked for. If any other community wants those, we can provide them. This is what's going to go into the archive. You can, of course, run the pipeline and get them yourself. This is my last slide. So if you're excited or motivated or upset that we've probably done something wrong and you want to correct it, if you want to contribute, you can easily talk to me or any of the other members of the calibration working group, and these are both instrument team members mainly are on this working group, both internal to the Institute and external to the Institute. If you're really motivated, join the calibration working group. This is a pretty open working group. I'm more than happy to give you an account on the Confluence pages. We keep these with all the details of the algorithms and the discussions that go into why we've picked a certain algorithm. And you can contribute. It is the reason we want, it's not completely open, is we would like your name attached to your comment so that we know who to talk to. And one of the things in particular is which optimal steps are particularly important, and that's the thing we're working on now, and that might be interesting. That's it. Thank you very much.